Recording. All right, so that's good. All right, so today's focus is going to be on structures. So there are a few ways to go about doing this. One is to go through some sample programs, and then the other one is just kind of talk about the theory. So what I will do is I will tell you where to find the discussion. So if you want to kind of really read the document about this, you can do so. It would be structures and arrays, and I want to make sure this is actually this class. It is. Okay, it's the correct class. So if you go to structures and arrays, that's the module that talks about structures and arrays, how basically they are organized in memory and so on and so forth. But instead of just going over the description and stuff like that, I'm going to go through some sample programs. Okay, so we'll take a look at a sample program, and at the end of the class, I will give you the zip file as well. I will unhide this one, which is okay. It is not the current one, but it's still gonna work. All right. So at this point, I am going to switch to the command line interface so that we can look at the C code, and then we look at the assembly code, and then I'll try to answer questions as necessary. But has anyone tried out the Chat GPT tutor, the TTP ASM tutor? Did you guys know about it? Okay, yeah, that should be. You should know about it through the announcement. So if you have not toyed with it yet, I would at least give it a try. Okay, it is experimental, which means it is something that I'm still working on. But if you go to this link here, you're going to go to TTP ASM tutor, which is a custom GPT. Okay, if you don't know what a custom GPT is, you can actually look it up, and you can make your own custom GPT if you want to. But you can also just kind of ask a question. It's like you can ask, describe, okay, how functions are called and how the callee returns in TTP ASM. So everything is in the context of TTP ASM. So it would actually naturally knows what kind of instructions to use. So it would tell you everything that you need to know about calling a function. Parameters are to be pushed, and then the return address, and then we have a JMPI instruction, and then inside the callee, the function being called, it has to set up the local variables. You can now access the parameters and the local variables, and the return is done by this, and this how the stack is laid out. In other words, what is in the frame. The caller pushes the parameters in reverse order, then the caller pushes the return address, and then the callee is responsible to allocate for local variables, and so on. And it will even give you some sample code, like this, with comments, to describe line by line, what it does. So I would say it's fairly good. Okay, I'm trying to spot errors, and occasionally it would, make some errors. So don't assume that this is going to give you the correct solution all the time, but it can at least give you some idea. If you ask it to describe a concept, most of the time it will get it right. Okay, so in the absence of office hours and it's the holidays and you just go like, okay, I just want to clarify one little thing, you can give it a try. Okay, so once again, no warranty is going to come with this custom GPT, and I am continuously trying to modify it just so that I can increase the accuracy and the completeness of its responses. But you can certainly give it a try. Okay, so it's a resource that is available to you. All right, and I specifically ask it not to give people an entire solution, so you cannot just give it some C code and expect it to give you the entire program. And if it does give you the entire program, there's no guarantee that the program is actually correct. But you can probably describe how it is not behaving correctly, and then the GPT engine may be able to help you figure out what's wrong with the code. So anyway, it's just one of the resources that's available. All right, so what we are doing today is we are going to take a look at linklist.c. So this is the C code that I want to talk about. And in this particular discussion, I will also have to talk about how structures are, what they look like in assembly language, and then, specific to TTP ASM, how do we make use of structures so that the caller, the callee, and all the initialized variables, they will all be, handled correctly. So we'll just look at the C code for now, and then we'll go through the C code, and then we'll switch to the assembly code so that we can say, okay, but how do we do the same thing in assembly code? All right, so this in the C code, from line 3 to line 7, that is the definition of a structure. The structure has a name called X. So X is not a variable. It is not using any memory when you run the program, because X, uppercase X in this case, is the name of the template. In other words, uppercase X is more or less like the name of a class, okay? Except your structure is kind of like a more limited version of a class. So with a structure, you can only have public members, and in C, you cannot have member functions. So you can only have member attributes like variables, quote unquote variables. So in this case, this particular structure has a first member called V. It is an 8-bit unsigned integer. And then the second member is called next. And next is a pointer to a struct X. And that's it. That's the entirety of this particular structure definition. Do we have any questions about the structure definition in C? No questions? Okay. All right. So then we move on to lines 9, 10, and 11. Okay, so let me move the cursor down over there. So line 9, 10, and 11, those are global variables. So N1, N2, N3, they are all global variables, and each one is also initialized. In other words, for N3, the first member, which is V, is initialized to 2. The second member, which is the pointer called next, is initialized to 0, which is the same as null. Okay, so NULL, all in uppercase, is really just 0. And 0 is one of those things where it has quote unquote universal type. So in this case, even though this 0 is specifying a value that is a pointer, there's no need for typecasting. Okay, because typically you cannot do this with any integer, but 0 is special. The compiler does automatically change the type in order to say, oh, okay, you mean this is a null pointer, and it just takes it. Okay. On the next line, we have something similar. The variable is N2. It is a global variable. The first member is V. It is initialized to 5. The second member, which is next, is initialized to the address of N3. Okay, the address of N3 does have a type of a pointer to a struct X, so there's no problem with type checking. And then the last one is N1. It is also a struct X. The first member V has a value of 16. The second member next has a value that is the address of N2. So the way you can look at this is, it's kind of like a linked list. Well, it is a linked list. So if you are taking CISP 430 right now, you probably recognize, oh, this is the kind of stuff that we talk about in CISP 430. You would be correct, okay? But what does this have anything to do with assembly language programming? Well, it's just translating the code. So I'm not going to ask you guys to write any C code to deal with data structures. Instead, I will provide the C code. Your only job is to translate the C code into assembly code. Is that okay? How many people have taken or is currently taking 430, CISP 430? So we got a few people, okay? So, but if you have not taken CISP 430, there's no need to worry, because our concern is simply the implementation, which is how do we translate the C code into assembly code. So in this case here, what we have is N1 kind of has two fields, okay? The first one is the value, and it is 16. N2 is kind of the same thing. It has two particular members. The first one is a 5, and then N3 is kind of the same thing. So this is typically how we draw, nodes on a linked list. So the third one has a value of 2. So what is interesting is the second member of the structure, which is a next pointer. So N1 points to N2, N2 has its next pointing to N3, and for N3, because it's a null pointer, so it depends on the textbook. Some textbooks just kind of give it a ground symbol to basically mean this is the end of the whole thing. I don't remember what all of the alternative symbols people use to represent a null pointer. But basically, it means N3 does not have a next. Are we doing okay so far with this picture? All right. So now, the other thing that is important is variables that are global variables, they do not live on the stack. So depending on the architecture, they can live in RAM that is outside of the stack, but yet it is separated from where the code is located. So that's typically true for a modern architecture, but for TTP, it basically lives within the same space as where the code is located. Okay. So now we go to main, which is the only function in this entire example. We have a local variable called pointer. Pointer has a type of a struct X pointer. We have array. The name is array. It is an array of 3 unsigned 8-bit integers. And then we have local variable I, which is just an unsigned 8-bit integer. The first line says I need to take the address of N1 and then store that into local variable PTR pointer. The second line says I need to initialize local variable I to 0. And then we have a loop. Line 20 to line 25 is a loop where we continue with the loop as long as pointer PTR is not null. On line 22, which is inside the body of the loop, we try to get to the value of member V of the structure that is in return pointed to by pointer as a local variable. We retrieve that value of the member, and then we store that to the element that is in array, okay, the array, and variable I is providing the index so that we can get to the correct element in the array. And then we proceed to increment I, okay, I gets I plus 1, and then this is the most interesting part of this entire program is here. Okay, we take the member next of the structure that is pointed to by PTR, and then we use that to update PTR itself. Okay. So do we have any questions about the C code? Okay, don't focus on the translation into assembly code or how things are represented in TTP. Just focus on the C code. Do we have any questions about the C code? Okay, I don't see any questions. All right. So if there are no questions, I am going to write the assembly code on the right-hand side. So let me go ahead and split the screen to 2. And then on this side, I will edit a new file, which is list2.ttp.asm, because I have gone through the original and also one additional version already. I will give you all the different versions, not a problem. All right, so in this code, because main is a function, I'm just going to call main. So no op, LDID with a 0, not necessary, but it's good to have it, to kind of emphasize that we're initializing the stack pointer. LDI A.6 plus. This is how we specify the return address in a call. And that depends on the sequence of instructions right after the LDI. So we decrement the STDA that will push the return address, and then the JMPI to continue execution in the function called main. When main returns, it should return to this halt instruction, which is what the the dot 6 plus is specifying. So if anyone is a little bit confused by why .6 plus works, okay, so can someone imagine what my recommendation is? Ask ChatGPT. Okay, it actually does a really good job explaining. Okay, so I'll illustrate it. Why not, right? All right, so if you go to ChatGPT, okay, this is my account, so you go to, or you follow the link that I provided in the announcement, and you can just click on this one. In a function call, how does .6 plus specify the return address? So because I know a lot of people have that question, so I basically have a pre-made question for this particular chat GPT, and it does give you a pretty good answer. And you can ask for clarifications as well. So this is the answer from chat GPT. So it explains everything. I'm reading the whole thing right now to make sure it is correct, and it is correct. So it even gives you some sample code, which is what we saw earlier. Okay, and okay. So now the question is why use 6? Okay, so you can ask how did you count to 6? And it will give you a full explanation of how it counts, why we use 6 as an offset, because it's all about how many bytes each instruction uses, and it will even explain what each instruction takes up in terms of the number of bytes, and therefore we have a 6 as an offset. Okay, I'll just put it this way. I'm actually pretty impressed by what it can do. Okay. All right, so getting back here. So now we can go ahead and continue with the definition of struct X. So struct X cannot be represented as a structure definition in assembly language because no assembly language actually supports the concept of a structure. But it doesn't mean that we cannot represent, where the structure of a structure. Okay, I know that sounds really weird. The first structure is a general word of the structure, and then the second word refers to the struct definition. So in this case, I'm going to define some labels. Each one is telling me the number of bytes as an offset to each member of a struct X from the beginning of the structure itself. Okay, so V being the first member of a structure is going to be at the very beginning of the entire structure. Okay, so that's 0. And then next is going to be, however, the number, the offset to the previous member plus the size of the previous member. Because V is an unsigned 8-bit integer, it takes up only 1 byte. So that means the starting point or the offset to the next, quote, next, end quote, member is going to be whatever offset V has and then plus 1 to it. And then we also need to keep track of the size of the structure. And to keep track of the size of the structure, it will be the offset to find the last member of the entire structure plus the size of the entire of that particular member, the last member of the structure. So this is how we basically define a structure in assembly language. Okay, do we have any questions about this? So this looks awfully, I would say, dry. Okay, so what you can do is to kind of give this a try in, especially the fact that the first member is at the very beginning of a structure. You can actually test it. Okay, you can go to online GDB and you'll really just compile a simple program. Okay, so we'll select C as a programming language here. And then we'll define the structure. Okay, so struct X, okay, the same thing. I cannot use my VI keystroke here. So we'll just say integer. Okay, nothing too special here. Struct X points to next. There we go. And then all we want to do is to say, okay, we have a local variable, struct X var1. Okay, and we'll say var1 dot v equals 20. Okay, I need this statement here because otherwise the C compiler would actually optimize unused local variables out of the whole thing. Then I cannot demonstrate what I wanted to demonstrate. The printf can go away. I don't need that. All right, so we are now going to test run this program, do a debug, and I'm missing expected identifier or open paren before end race on line 16. Oh, that's an extra one. There we go. Thank you. All right, so I'm going to put a breakpoint on line 20. Okay, so we'll just go ahead and run the program all the way to line 20. The only thing I wanted to tell me is where is var1, okay? And I want to turn off your syntax highlighting because it does make it a little bit harder to see it. So we say set style enabled off. And then now we can say print, where do I find var1? Okay, some kind of address ending with a 30. So now I can ask it again, where do I find var1 dot v, which is the first member of the entire structure? Same place. So that's a confirmation, right? This is a confirmation that the address of the first member of a structure is the same as the beginning of the entire structure, which kind of makes sense, okay? Now, the next item is always going to be a little bit after that. So we just click what is next. So now, why is it off by 8 bytes? Well, there are a few reasons, okay? One reason has to do with how big is an int for this particular compiler. It may be a 64-bit integer, but the other thing has to do with alignment. Okay, so when you're working with a modern computer architecture where one single memory fetch can grab 8 bytes at a time, alignment becomes an issue. It is not so much an issue of whether it's going to do things correctly or not. It is an efficiency kind of thing. Okay, but for TTP, you don't have to worry about that at all because it's a byte-wide type of memory organization. So we don't have to deal with that. But in case you want to confirm how wide or how many bytes an integer is going to take, you can always ask that question. So in this case, an int only takes up 4 bytes, but yet the next pointer is 8 bytes off, but that's because the architecture itself is a 64-bit architecture. So in order to optimize how the number of memory access in order to grab something, we want everything to be along the border of an 8-byte thing. So that's kind of why it takes up 8 bytes instead of just 4 bytes. But once again, in TTP, we don't have to worry about that because the memory bus is only 8-bit wide. All right, so now we are done with the structure definition itself. Do we have any questions about line 9, 10, and 11? Those are just label definitions so that we can have labels to designate the offset of where we can find each member in a struct X. Are we okay so far? All right. So now we move on to line 9, 10, and 11. So on line 9, we are defining N3. So the way we define global variables in TTP is really just use a label as the name of the global variable. And then if we need a byte that has the content of 2, that's what we do. Okay, so that's what the byte directive is for, is to say, oh, I don't know what this location is for, but somebody told me that this byte should have a value of 2, the next byte should have a value of 0. So we do the same thing with N2. So byte 5, and then byte N3. So that's all we need because the label is the address. Okay, so N3 as a label is defined to be the address of the byte 2 on line 14. So that's why a reference to the label gives me the address that I need when I'm defining N2 or the next member of N2. And now we can move on to N1. And N1 has 16 as the V member, and it also needs to refer to the address of N2. So that's how we do the reference. So that means we are now done with the initialization of the global variables N1, N2, and N3. Do we have any questions about in the assembly code from line 13 all the way to line 21? No questions? Okay, all right. So now we are ready to implement main. And from this point on, I am going to be very systematic when it comes to the calculation of what items are in the frame and how do we get to each item in the frame. So a frame consists of all the local variables, the return address, and all the parameters. In this case, PTR is the first local variable. So it is at the base of the entire frame. And then we have array, which is right after PTR. So we use the offset to PTR and add the size of a PTR, which is just 1 byte, to get to the offset of array. And now we have I. I is going to be based on the offset to the previous local variable, which is array, plus the size of the array. The array has 3 elements. Each element is only 1 byte wide, so that means the entire array uses up 3 bytes, and that's why we have a 3 plus here, because the array itself has a size of 3. And then we have main LVS, which stands for local variable size. It is a label so that I can keep track of how many bytes I need to allocate for all the local variables. So that would be the offset to the very last local variable plus the size of the very last local variable. So that's I, and then we add 1 to it. So these are all the label definitions. Label definitions by themselves do not do a single thing to the stack pointer or anything on the stack. So that means I have to utilize these labels in order to allocate space for the local variables, and then later on to also deallocate the space for the local variables. So the typical code that I use here is going to be just LDIB with, or whatever, A, B, or C is fine in this context. So we load main LVS, which is the number of bytes that we need to reserve for local variables, and then we subtract that much from the stack pointer. That's how we allocate. And then to deallocate, we do basically the same thing, except we add this much back to the stack pointer. And then while we are here, at this point, we should have the return address pointed to by the stack pointer. So that means when this is also a time to return to the caller. So that means I have the usual LD BD, okay, because we're retrieving the return address from where the stack pointer points to. Increment D, because according to the caller-callee agreement, it is the responsibility of the callee to deallocate or pop the return address, and then JMPB in order to continue execution at the caller. So are we doing okay so far with the shell or the framework of main? And this is the typical way that I write my code. I don't usually write my code from the first line all the way to the last line. I do it by structure. So when I open something, I close it almost immediately so that I don't forget about doing it. But are there any questions about the shell of main itself here? Okay. If there are no questions, we will go ahead and implement line 18 of the C code. So when we look at line 18, which is an assignment operation, we have to figure out the right-hand side and then the left-hand side. Typically, you want to figure out the right-hand side first, because without knowing what the right-hand side is, you really don't have anything to store to the left-hand side. So that's why usually we look at the right-hand side. In this case, the right-hand side is easy. That's it. Because N1 as a label is the address of global variable N1, because it is not on the stack. Okay, N1 as a global variable, which is defined on line 11 in the C code, is not on the stack. So there's no need to add the stack pointer to N1 at all. So I just want to confirm, do we understand that? The way we access a global variable or a static local variable does not involve the stack pointer, because those items are not on the stack. Is that okay? All right. So now we need to compute where do we want to store that. So on the left-hand side of line 18 in the C code, we are specifying PTR, and PTR is a local variable, and it is not a static one. So that means what main underscore PTR really is the number of bytes between PTR from the base of a frame. Okay, so I'm going to do this first, but I want to explain later on, like right away, what the frame is going to look like in this case, in main. I can do that with a picture. Okay, so I'm going to do it in a picture here. So that means the frame of main is going to look like this. So this is my attempt to use text to approximate the picture. At the very top is the return address. In other words, this is pushed by the caller, and as a result, it's the first item pushed or allocated, and as a result, it has the highest memory address. The next items are from the local, from main itself. So the very next item is going to be local variable I of main, because it is the last local variable. And then next to that is going to be array bracket 2, which is the last member of the array. And then we have the second last member of array over here. And then we have the first member of array over here. And then we have the local variable PTR here. So this collectively is the frame in this case, in this particular call to main. And when everything is, this is the base of the frame, okay? This is the frame base. Is that okay? In other words, the way we define the frame consists of, the storage for all the local variables, the return address, and parameters. But in this case, main does not have any parameters, and as a result, the last location of this frame ends with the return address. But if main had parameters, those parameters would have higher addresses past the return address. So collectively, all of these items, all of these bytes become the frame for main when we invoke or call main. So this is the frame base. And after we do all the allocation, we also want the stack pointer to point to this location. So that means, after this instruction here, that's exactly what will happen. But before lines 37 and line 38, the stack pointer was here, okay? Stack pointer at the entry point of main is going to be here. So main itself is responsible to move the stack pointer down by 5 bytes so that we have those 5 bytes allocated for my local variables. All right, so getting back to what we need to do, this is just the offset, and then add BD will end up with the address, and then STBA will store N1, the address of N1 as a global variable, into the local variable PTR pointer. All right, do we have any questions about this code? No questions? All right. So then we shall move on to the next one, which is initializing I with a 0. Kind of the same deal. Okay, the right-hand side is super easy to compute. The left-hand side is referring to a local variable. So we always get to the offset first, and then get to the address, and then store to the address of I, what we have already computed for the right-hand side, which is just a plain 0. So that would accomplish line 19. And then we have a loop. So when I implement a loop, I would practice the same thing, which is the bracket approach. Start with the structure and then backfill what is supposed to be inside the structure. This is the first loop, so I'm going to call this loop while 0. And then this is the beginning of the whole thing. And every loop has an end as well. So I will start with defining the begin label and the end label for a loop. And I will also automatically put in an unconditional branch right before the end label to go to the begin label. Because this is the behavior of a while loop, is after you perform one iteration, you always go back to the beginning and say, okay, is it time to leave this loop or not? So that's the basic general loop structure. Now I have to put in the logic to say, okay, when do I get out of this loop? So if PTR is the only condition in the while loop, what is the condition to get out of the loop? That's a C++ question. Yes. When PTR is null, or when it is a 0. Okay, so that's good. So that means we have to access PTR first. So we already know how to do that, okay, from the earlier code. So it's a LDI, you can use whatever register A works in this case. This is the offset, this is the address, and this is the actual PTR. Okay, and now we have to compare to see if it is 0. Now I can use compare, okay, but I can also just use AND AA. Okay, so AND AA is one of those things that we talked about in one of the labs. It is a very easy to use shortcut. If all you care is whether register A is a 0 or not, and you're not comparing it to a very specific value, then this mechanism will force the value of A through the ALU and therefore changing the Z and the S flag. So that's why I can now rely on the Z flag and say, hey, if A is a 0, which means the Z flag is a 1, let's go to while 0 end, okay, because that's how we exit the loop. So that means on line 52 right now, that's going to be the body of the loop. Okay, so what we need to do from line 22 to line 24 in the C code goes to where line 52 is currently, where the blinky cursor is. So do we have any questions about this? Okay, so once again, you can see how the way I write the code is not linear. I go by the structure of the code. Okay, so if you find it to be reasonable, you can also try to practice the same thing when you are working on the homework assignment. And by the end of this class, there will be 3 active homework assignments, which sounds like a lot. But the more you write, the quicker you will be able to do it, for the other 2. So that's kind of my hope is, you will that the whole process will accelerate because you're getting more familiarized with not only the instruction set, but also the techniques that you need in order to debug your program. Which also means people who try to procrastinate as much as they possibly can for the first homework assignment. I'm hesitating to say this, but I think I really should be honest, are doomed for the other 2 homework assignments. Okay, so try to get on to the first homework assignment as soon as possible, because what you learn from the first homework assignment would also apply to the other 2 homework assignments. All right, so now what do we do with line 22? So line 22, you have to think about this in dependency, okay? In other words, you look at these operations and you ask, okay, we got a bunch of stuff that we need to do. We have indexing, we have assignment, and then we have to access the value of a member of a structure that is pointed to by a pointer that is a local variable. So you got a whole lot of stuff, right? So now you have to look at the dependency. It's like, okay, with the operations, which one cannot be done until I have these things? Oh, I cannot do the assignment until I have the right-hand side and the left-hand side figured out. Okay, cool. So that means don't worry about the assignment. Okay. The right-hand side and the left-hand side can be worked out kind of individually. They can be done, because they're not dependent on each other. So we'll just focus on the right-hand side, which is a typical approach, is to work out the right-hand side first. So the right-hand side by itself, okay, how you specify that expression, okay, let me highlight the expression on the screen so that people who are watching this video can understand what I'm referring to, okay, which is this part here. How you say this is really important, okay? Some people just say, oh, this is pointer points to V. That doesn't tell you how to get to it. But if you say this is the value of member V of the structure that is pointed to by PTR, which is a local variable, that basically tells you everything that you need in order to work out the instructions. So how you describe an expression is very important. The more precise you describe the expression, the more likely you can work out all the dependencies and figure out, oh, okay, I need to get to this first, and then we get to this, and then we get to this, and so on and so forth. So in this case, okay, let me just write it out, okay, because I did this with my Tuesday, Thursday class too. So I'm just going to write out here, okay, on the other side. So right now, okay, I will comment and say PTR points to V. So what is this? This is the value of member V of the structure that is pointed to by PTR PTR is a local variable. Okay, so that is as accurate as I can do to describe it. All right, so every time you see of, okay, so you can see the value of something. So that means I cannot get to the value until I get to the, in this case, the address. But I cannot get to the member until I get to where the structure is. I cannot get to where the structure is until I know, what pointer has as a value. I cannot get to what pointer has as a value until I get to the address of the pointer. I cannot get to the address of the member of pointer until I know how many bytes it is off from the base of the frame. Do I know do I know how many bytes is pointer from the base of the frame? Yes, I have a label just for that. So let's start with that. Yes.
Line 19, where do you define it on the right side?
Line 19? I might have forgotten. Huh. I thought I did that. Maybe I did it. Oh, okay. I put it in the wrong spot. In other words, I put the loop onto the wrong spot. Let me change that. So we can specify line 60 to line 64. Move that, I think it's just M, move to line 44. There we go. I like VI because that you can actually type commands in VI. All right, but thank you for the reminder, okay, because otherwise the loop is not going to work. All right, so based on what I just said about this portion here, the first thing I need to, the only one thing that I know is the offset to get to PTR in the frame. Okay, that's just the offset. Okay, LDI A main PTR, that's the offset. And then at this point, the stack pointer is pointing to the base of the entire frame, which means if I just add the stack pointer to the offset, I'm going to get the address. So add AD, that's the address of pointer. I need to get to the content, the value of pointer, so I need a dereference. Now I have pointer, the value of pointer in register A. That is the address of a structure. I don't need the entire structure. I need to get to member V of the entire structure. Okay, I know the offset, okay, from the beginning of the entire structure to member V, which is represented by X underscore V in this case. So I just need to add that much to the address of the structure itself. So now register A has the address of member V of the structure that is pointed to by PTR. But I'm still one step, from what I really need to specify the right-hand side of line 22 in the C code, because right now I have the address of that member. I need the value of that member because I don't see an ampersand in this expression here. So I'm not looking, I don't want the address. I want the actual value of member V. So that means I need one more dereference in this case with register A. Okay, so that code from line 60 to line 65 of the assembly code is accomplishing getting the right-hand side of the assignment on line 22 in the C code. Are we doing okay so far with that? Okay, so essentially, it is, you just have to really keep track of what is in a register after each instruction. Okay, if I were you, I would try not to, okay, emphasizing not, to memorize these sequences and say, okay, this translates to that, memorize it, okay? Because in the final exam, I can give you alternative sequences of instructions that can get the same thing done. So if the sequence does not look the same anymore, can you still recognize what it is going to do? So memorization is not going to help you in that case. Okay, understanding how it works does help. Okay, but memorizing it is not going to be too helpful. All right, so what about the left-hand side? So the left-hand side gets a little bit complicated because we are dealing with array indexing here. The nice part about this particular array is every element is only 1 byte wide. So that means each element is only 1 byte away from the next element. You go like, okay, how do we know? How do I know that? Can I visualize it? The answer is yeah, absolutely. You can visualize all that. So we are going to, kind of change this program a little bit, and we just say, okay, I have to pound include stdint.h so that I can reference, the type that I need to reference here. So uint8 underscore t array 3, okay, same as the code. And then we have to say array bracket 0 equals to 2. Okay, doesn't matter. I just have to use the local variable in order for the compiler not to optimize it out. Okay, so we move the breakpoint over here, and then we go for another debug session. Run the code, and then we say set style this enabled off. There we go. Okay, so now I ask, where is array? Okay, you can actually say, ampersand, it doesn't really make a difference. Okay, it is at blah, 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 3, 5. Then you can ask, where is the first element of array? So give me the address of the first element of array, and it is at exactly the same location, 3, 5, and 3, 5. Then you ask, where is the second one? What is the address of array bracket 1, which is the address of the second element, and it's exactly 1 byte after that. So that means in this context, all we have to do is to figure out what I has as a local variable, and then we add that much to this address of the entire array, and then we'll get to the address of element I of this array. Okay, so that means I need to get to I. Okay, let's get to I first. LDI, I cannot use register A anymore because it is holding the value of the right hand side. I still have two more registers to play with, so I think I'll be fine here. Add BD, LDBB. So now register B has the value of local variable I. And then next, I have to figure out where is array in the memory. So I'm going to use basically the same approach. So now register C has the address of array. If I add the value of I to the address of array, then I should have the address of element I of the array. So I just need a add instruction here. Doesn't really matter which way I add. Okay, I'm gonna do an add CB. So register C should be the address of element I of array, which is where the entire left-hand side is trying to specify. So that means I'm ready for store. Register C contains the address of where I'm supposed to store, and then register A has the value of the entire right-hand side, which is what I need to store. So that should complete what line 22 is supposed to do. So right now, I have written a whole lot of lines without debugging it at all, okay? So if you are doing this, this is not recommended, okay? I do not recommend anyone to write this many lines of code without running anything and testing it. But you guys go like, but the program is not done. How am I supposed to test it? Easy. Put a halt instruction here. Just make the whole program stop right here, okay? This is a very crude way of making a breakpoint that cannot be continued past this point, okay? Which is okay, I mean, it's not a big deal, because all I want to do is to say, okay, do I know what is supposed to be in memory at which location, and so on and so forth. So I have a picture already kind of describing this here from the other class. So let me see if I can, okay, I'll just make a new one for this class. Okay, so I go to the share folder and create a new spreadsheet with today's date on it. So that means, when you look up, the spreadsheets, just look for today's date, which is 2024-11-27. And, on the column A is going to be the addresses in decimal. So this location is just this location -1. And then we'll just, kind of allocate a bunch of these, okay? This is probably more than what I need. Column B is just going to be the hexadecimal representation of that. So there's a method called, dec decimal to hexadecimal, in Google Sheets. Kind of handy. There are several ways to do this, but this is one of those many ways. Okay, so this way I have all of these addresses in hexadecimal, which is handy. And now I want to describe what is at each location. FF is the first thing that I push on the stack. That is the return address. It's the return address back from main to the entry code. That's the very first thing that I push on the stack. And then the next 5 locations, meaning these 5 locations, are the local variables. So the local variables, according to the way they are declared, I think PTR is the first one, and then we have the array, which has 3 elements. And then finally, we have local variable I. So now I know which location is supposed to be used in what particular role. So now I go like, okay, but do we know the values? At this point, where I get to the halt instruction. The return address is in hexadecimal 09. Okay, I know because I've done this enough times. Okay, the way that we have done the entry code is always the same. So the return address to the halt instruction in the entry code is always 09. I is supposed to be initialized to 0. Okay, so we should still have 0 over here. And pointer is initialized to the address of N1. I'm just going to use address of N1 here because I have not assembled the program. I really don't know exactly where that's going to go. And in this case, we would have stored the value of N1 to element 0 of array. The value of N1 is 16, which is in hexadecimal 0x10, or just quote 10. So everything in column D are in hexadecimal. Because in base 16, 10 is representing what we know as 16. So this is what I'm expecting the program to do, okay? And now we go to, let's go here, and we'll go ahead and submit the program. Okay, this is list2.ttp-asm, and I forgot to save the file, typical of me. Okay, save. Let's do it again. So once again, if you have not gotten Reefer Spider to work, in the lab time today, I'm fairly sure that we'll have enough time today. I can help you set it up, okay? Because it's really, really important that you get it to work first. All right, so we get to the analysis tab. We just do a refresh. Okay, so we now look for memory updates, which is reflected by column C. So column C says the first thing we do is to change the content at location FF to 09. Okay, well, I think that's consistent with what we expected to do. And then what? And you scroll down, okay, location FA should be 0E. So if you go back to the map here, location FA is supposed to be the address of N1, which means how do we know whether that's true or not? You go to the Assemble tab. So in the Assemble tab, you just have to look up the label. And in this case, the label is N1. And N1 is the label of the next location. The next location has an address of 0E in hexadecimal. So that is correct. I have just verified that 0E going into location FA is in fact correct. Okay, so now we go like, okay, so proceeding, okay, further, what do we see? What are we supposed to see? Location FE should get the value of 0, 0. So we first want to know who is supposed to be there. Local variable I. We are expecting it to be initialized to 0, so everything is going according to plan. And then what else? Okay, so we are expecting another write operation, which is this one. FB, location FB is supposed to get a value of 10 in hexadecimal. And that's also expected because location FB is the address of the first element of array. And that's where the halt instruction is. Okay, after we basically completed the code up to that point. All right, so do we have any questions at this point?
Just to make sure you healthy on the first iteration, right?
No, I'm not even done. I'm not even done with the loop. The loop is currently done with only line 22.
Right. Just
Yeah, so we only got line 22 done, currently in the loop. Yep, yep. hmm But the way I verified that everything is working up to this point, that is important. Okay, it's important in two ways. One is how I did it. Okay, the way I use a map to figure out what is supposed to be at which location and what value it is supposed to get. That is important. Having a model of what the program is supposed to do in your mind, you can use a piece of paper, use a piece of paper or spreadsheet to help you out. Okay, but ultimately, you should know how to work out what the program is supposed to store at which location. Okay, because without that, there's no way you can check whether your program is doing it correctly or not. Because without this map here, I cannot go back to the trace and say, oh yeah, I'm supposed to be seeing a 1-0 at location FB. So that means without this picture, I cannot really check whether my code is working correctly or not. Okay, so you gotta be able to do this kind of on a piece of paper, in your mind, using a spreadsheet. Use whatever means that works best for you. For me, a spreadsheet works well because it's just a table. But if you wanted to use a piece of paper, that works too. All right, so now that we know it's working up to that point, I can now continue, which means getting rid of the halt instruction and then continue with the next statement, which is incrementing the value of I. So I cannot get to the value of I unless I get to the address of I. So this is one thing that most people need some time to adjust to from CISP 360, because in CISP 360, in almost every single high-level programming language, getting to the value of something is simpler getting to the address of something. Because in C++, if you want to get to the address of something, you have to say the ampersand and then something, right? But in assembly language programming, it is exactly the reverse. You cannot get to the value of something unless you know where it is. So getting to the address first is actually the natural way of flowing in a program, because you need the address in order to get to the content, in order to get to the value. All right, so that means, okay, I need to get to the address, but to get to the address, I have to get to the offset first, and then adding the stack pointer to the offset would give me the address. And then I do LDBA in this case. So the B is the value of local variable I. Increment B, okay, because after all, line 23 of the C code is supposed to increase the value of I by 1, and then store it back to wherever A is pointing to, because register A still has the address of I. So this sequence of instruction will increment the value of I. Okay, so do I know whether this works or not? No, okay. So we'll make the assumption that, yeah, I might have made mistakes here somewhere, okay. I need to double check. So to double check this means I'm going to go back to the map, which is, oh, we are on that slide already. So it is supposed to change this 0, 0 into a 0, 1. If I could do a strikeout partially on the line and then continue the rest, I would have done that, but I don't think that is possible. I can give it a try. So select the two characters that I need to strike out and then go to, where should I go? Oh, right here, text, strike out. And it strikes out the entire thing, which is not what I intend to do. So I can try the keyboard shortcut too. Okay, so we go to here, Alt-Shift-5. Okay, so we'll see whether that works or not. So we just select this portion, Alt-Shift-F5. Okay, press the enter, nothing happens. Okay, let's try that one more time. Alt-Shift, was it 5 or Alt? Oh, that works. Okay, I learned something today. Okay, you can actually make part of a line, strike out or struck out, because you just have to use the keyboard shortcut, cannot use the menu. If you use the menu, it applies to the entire cell. Okay, cool. Okay, this is nice. Because now I can say, okay, this is what I'm expecting the program to do. Go back to the text prompt, save the program, because I have a bad habit of not saving it, and then run it again. So River Spider is nice because all you need is the up arrow, press the enter key, and the whole program runs again. Now, it might take a little bit of time, like a few seconds to run, but the nice thing is you don't have to pay attention when it's running. So now I'm looking for an update to location FE. I found it, and everything is verified. Nice. Okay. So the next thing I need to do, okay, according to the C code, is the last assignment in the loop, which is taking the value of the next member, I should say member next, member next of the structure that is pointed to by PTR, and then use that to update PTR itself. So when the code in C may look a little bit confusing because it seems like we are pulling the rug from under ourselves, because after all, this pointer is supposed to be the same as that pointer. But the order of operation is clear. The right-hand side evaluates first. Whatever it is used to update the left-hand side. So by the time we update the left-hand side, I don't really need to know what pointer was pointing to because it is irrelevant at that point. Okay, so we'll go ahead and do that. We need to get to pointer first. So that means we need to get to the offset of the pointer. Then we need to get to the address of pointer. Then we need to get to the actual pointer, the value of the pointer, because the value of pointer, PTR, is the address of a structure. Okay, so now we have the address of the structure in register A, and then we use another register to store the offset to member next in number of bytes from the beginning of the structure. Add these two. Okay, now which way you add? Well, let's see. I'll do a little bit of an optimization here. So instead of putting this into register A, I'll put it into register C because I have enough registers for this optimization. So register C has the address of the structure. Register B has the offset from the beginning of the structure to the member that I need to access. So I can now do an add CB. So that becomes the address of member next of the structure the pointer is pointing to. But that's also not what I want because I need the actual value of member next. So that means I need to do a load CC. So now I have the entire right-hand side computed in register C. The left-hand side specifies I need to store back to pointer, but I still have the address of pointer in one of the registers. Okay, I'll let you guys decide which register still has the address of local variable PTR in it. All three registers were used in this code. Register A, very good, nice. So if I were you, after this class, I'll go back because I will give you this code. I'll go back and comment all of this code, okay? Because that's how you can practice, to recognize, oh, okay, so this is how we compute blah, blah, blah. And this register currently has this value and so on. So if I do STAC, that should accomplish what we need to do. And once again, I'm not really sure whether that is the case. I'm going to put a hold instruction here. So according to this code, okay, in the very first iteration of the for loop, I should have put the address of N2 into pointer because the address of N2 is the value of member next of the structure of N1. So that means I'm anticipating in this trace here, I'm going to do the same trick here. So instead of having the address of N1, we now should have the address of N2. But I'm going to use the same trick to strike out this one. I think it's Control, or is it Alt or Control? Okay, I cannot remember. So let's double check. Alt. Okay, Alt Shift 5. So now we go back here, highlight the portion that I need to strike out, which is just this portion. Alt Shift 5. There we go. Nice. Okay, so this is the update that I'm expecting to see. Otherwise, the code is the same, so we should still have the same trace as before. So I go back here, Make sure I save this code before I run it, and then switch back to the command line that has everything already set up to run River Spider, and then just let it run. And then we go back to the assembler, go to the trace, and continue with the trace here. So now this is the update, okay? Are we updating the correct location? In other words, is FA the location that should be updated? According to this, FA really is the pointer, the local variable pointer. So we're updating the correct location. The next question is, are we using the right value to update it? In other words, is 0C the address of N2? So to know that, we kind of have to go back to the assemble view and then just locate how N2 is defined. This is N2, and it really is defined to be 0C in this case. So that means I have now double checked everything to be working in this trace. All right, but I have finished the program too. I really have completed the entire program, even though I put a halt instruction all the way down here. So in other words, what I have done so far is I have put what I would call a inevitable and non-passable breakpoint after line 24. But since everything is working up to this point, I'm just going to remove the halt instruction so the program can actually loop through the loop itself. Okay, so I'm going to take out the halt instruction like so, save the program, and then run it. So this time, if I run the program, what am I supposed to see? So to get to that, okay, first of all, let's just go ahead and run it first. So to understand what the C code does overall speaking, you can run the C code in online GDB or just regular GDB or code blocks or VS Code. Whatever environment that supports a debugger is fine, okay? So let me illustrate what I mean by that. So let's see here. Okay, I'll go back here and just copy and paste the C code. So that's xclip-shell clip redirect list.c. So all this does is to copy the C program into my clipboard. And now we go back here, paste the whole program in here, and then put a breakpoint at the very end. Okay, so I'll put a breakpoint here, get rid of this breakpoint, debug the program, and say run. So now we're at this breakpoint, which means the whole thing is done. So now I can examine the program line by, variable by variable. I can now say, what is supposed to be in I right now? I has a value of 3, which makes sense, okay, because we iterate through the loop exactly 3 times. I got incremented 3 times, okay? What about PTR? PTR is null, because otherwise we would not have exited the loop to begin with. And then I would say, what is supposed to be the first element of array? It's the value, it's the V member of the first node, which is 16, which is 10 in hexadecimal. And then I'll print the other one too, okay? Okay, excuse me, this is supposed to be 1. So we got the 5, and then we should get the 2, like so. So that means if I translate everything to the map that we were using earlier, so that means the final state of everything would have I being 3. So this would be 0, 3, and then this portion would all get struck out. Control Alt 5, Control Alt 5 again. There we go. This would be 0, 5. Okay, quote 0, 5. And then this would be quote 0, 2. And this would be null. So that means it's just 0, 0. So we get rid of all of these. Alt Shift 5. And then do it one more time to put it back in. Alt Shift 5. There we go. So this is what I'm expecting the memory space to look like, okay? Just based on the observation of what the C program actually did in GDB. So now the question is, does it actually do that? So we go back to the command line interface, make sure I save this code first, and then go back and just run the River Spider again. just so that we can get a confirmation, right? Okay, it's all done. Now we switch back to the assembler, go to the analysis tab, and then we just look for all those updates in the analysis tab. So we look at FA, okay. FC is getting 0.5, okay, we'll double check that. FC is getting 0.5, yep, that was expected.
You still gotta put
What?
N3, don't you?
Huh? What?
On line 60 on the previous spreadsheet.
You mean this one?
Yeah, on line 6, you still have to add 10% N3 before
No, it's supposed to be 0 now because I'm done with the entire loop. I ran the whole program. I did not put a breakpoint in the next iteration.
But you still have to assign the N3 though, right? Because the N3 will be the N3 of the 0,
Yeah,
2.
but the next of N3 is null, which is the last value that I used to update PDR. Because otherwise I wouldn't be out of the loop. Because N3, the address of N3 is not null. And, okay, so let me switch back to the code here. The address of N3 is not null, but I'm not going to exit the loop until PTR is null. So by the time I get to the return statement, PTR has to be null. It has to be 0.
But N2 is not never going to be null. N3 is the one that gets to be null, right?
No, N3 itself is not null. N3 has a member. It's the next member of N3 is null. But since in the debugger, look at where we are at in the debugger. We are already on line 26 in the debugger, which means we are already outside of the loop. And the only way to exit the loop is for PTR to become null. In other words, you are correct that PTR was once the address of N3, but we are past that stage already. You will see it actually, okay? So keep that thought in your mind. We'll actually see it. So if we keep tracking this, okay, keep scrolling down, this is a variable I, okay, it becomes 0, 2, okay, this is in the second iteration, and we see that FA becomes 0A. So what does that mean? FA is PTR, and becoming 0A means it is now the address of N3. So you are correct that it did update to the address of N3, but this is not the end of the trace. Because when the trace keeps going, FD is getting 0, 2. FD is the last element of array getting 0, 2 that we expected. And then the next update is FE getting 3. FE is our local variable I. Getting 3 is also what we expected. But now, the next member of the structure that PTR is pointing to has a null next. That is when this is the last update of PTR. So that's why FA getting a 0, 0 is ultimately what happens when the program terminates. Does that make sense?
No, it does. I just felt like it needed to be represented because you do execute the part where you change the pointer to the N3.
I do not, because it all depends how this picture is supposed to look like. Depends on where I'm supposed to look, because I'm already assuming that we are looking at memory content by the time we get to the return 0 statement in C. So that means we are already done with the loop. Is that okay? But we did see how everything got updated in between. It's just that by the time everything is done, we did end up with a value of 0, 0 in the pointer. But you are correct that in order to get here, it became the address of N3 first before it became 0, 0. So you are correct about that. But it's not represented because I kind of skipped the tracing of the entire loop, and I just say, okay, let's go all the way to the end here and see if that is what happened. All right. So at this point, I think we have just verified everything is consistent. In other words, I was able to explain how this code got to this state, which is consistent with what we observed in the C code. That is how I would imagine most of you, this is how you're going to work on the next homework assignment, which is the structured one. That one is also due in 2 weeks. Okay, so that means it is going to be due on the, I think it's the second to the last day of right before the final exams. 2 weeks is should be enough time, okay? Because normally in a normal semester, people only got about a week to work on these programs, okay? And that's before we have ChatGPT as a robo tutor. But you also have human tutors for this class. There are 2 human tutors for this class. The first one is in Mesa. So if you are a Mesa member, okay, you can be a half member, and still have access to the tutor. So his name is Marco. Okay, so go to the Mesa Center and ask for Marco, to be your tutor. He knows this particular class really well. The other person is, I think, Aubrey. Okay, he works in the LRC as a tutor over there. So that one, I think there was an announcement for that particular tutor. So those are the 2 human tutors that we have for this class. On top of that, you also have ChatGPT as an additional backup resource if you want to just kind of ask it some questions. All right. So let me talk about the homework assignment a little bit, okay? Because I just want to give you some overall ideas of what you can do. It's really simple, okay? It will take me like 20 seconds to do it. Okay. So the lab is already opened up for today's lab. Okay, so let me go to the lab first. So this is the lab that we're going to do today. It is called structures and pointers. So this is the easy part. It only has 3 points, okay? Most people are done in like almost no time. This is the part that is due in 2 weeks, okay? So that's why it's due on the 11th of December. And the instructions is pretty simple. Start with the file that is contained in the zip file, download, unzip it, look at all the files, and watch the video, okay? So I cannot overemphasize this part here. Watch the video, which has a certain repetition of what we just talked about, but it also has some guidance of how to get started with the Traverse program. Okay, so that part is super important. The entire video is about 40 minutes long or so, okay, just a little more than 40 minutes. But it's very dense, okay, just like most of the things that I do, it is very dense in terms of density of information. So that means you might need to kind of pause it from time to time, make sure that you absorb all the information before proceeding. And also the lecture today is also recorded, okay, which is nice because I forgot to turn on the recorder yesterday, and that was not good. Okay, that's the whole reason why I have this video recorded again yesterday. All right, so questions. Are there any questions? How many people have tried out the ChatGPT thing? Okay, if you don't need to, do not feel compelled. Okay, there's no need to check it out unless you think, I want to check it out just to see if I can get some instructions or get some pointers, get some guidance of how to get things started. It does a fairly good job, okay, explaining things to. Okay, let me illustrate what I mean by that, because some people are kind of skeptical about that. So let me go to this thing here. It's already there. Okay, explain how to access the value of a member of a structure that is pointed to by a pointer, a local variable pointer. Local variable. Yeah, Grammarly is kind of blocking the view of what I need to see here. Local variable pointer to a structure. Okay, there we go. And okay, I will check out the response. So it gives you an example of a structure definition, and then it will kind of give you an example of a C code or C program, and then it will give you the assembly equivalent of all the label definitions, the offset, from the frame of where you can get to PTR, and it really just explains things, step by step, with full comment and all that stuff. And then after that, it also has just complete explanation in the text. But I also instruct this particular GPT not to give people solution to homework assignments. So it does not give you like complete solution to homework assignments, but it does something like that, okay, which I think is helpful, okay, especially for people who kind of maybe feeling a little bit lost in the lecture. This part can be useful. So there we have all the resources available. And you don't have to pay ChatGPT $20 a month either. It just kind of limits how many times you can ask questions on a kind of time basis. So you might, I mean, even if you pay $20, I still run out of resources sometimes. Just yesterday, ChatGPT told me you have to wait an hour before you can do anything further, because I was kind of playing with this a lot yesterday, and I chewed up enough processing time. I probably burned through a whole case of your water bottles worth of water. And then ChatGPT goes like, okay, hold on a second here, cool down here. Don't come back until I think it was 10, 11 or something like that. Anyway, any questions? No questions? All right. So I am going to stop the recorder, upload the video from today, and then you guys can continue